My name is Saar, and this is a joint work with Maya, Dotan, Yossi, Gilad, and Aviv Zohar. They're all in this room. Okay, so Twilight. Twilight is a differentially private payment channel network. So first, let me introduce what payment channel network is. So first of all, this is a network. So we have relays, which are the participants in the network. We have channels. Channels are the edges in this network, which are locked coins between two relays. So for example, here we have two relays, each one of them locked 5 coins, and then they can just transfer 2 coins from one to another, which is just redivide the same locked coins. Great, and we have routes. Routes is a list of channels from a specific source to a specific target, and payments. Payments is just using this route to shift coins across it. So for example, if Alice wants to transfer 2 coins to Charlie in this example, so we can just adjust the division of the funds, of the locked funds, throughout the route. An important thing to notice here is that if Alice will want to transfer 2 more coins to Charlie, it will be impossible, because in one of the channels in between, there is not enough liquidity, and this is the one that is currently circled there. And payment channel networks is not something that I just invented. The main example here is the Lightning Network, which currently has over $100 million in locked funds. So this is a big thing that we really need to consider. And PCNs, payment channel networks, are great, but they're not private. In 2017, a probing attack was presented to our community, which based on the idea that query is cheap. An attacker can just repeatedly query the same channel over and over again over time and observe liquidity changes. So for example, let's say that the attacker uses the route that is now presented in blue, and he asks, hey, can I transfer 100 coins? And he gets yes from the network in this example, and he will not actually transfer these 100 coins. Cool. So maybe he can do it again and again, and see the question eventually changes. So for example, in here, he just got yes, yes, yes. No, something changed in the network. So in this case, he can just ask, hey, maybe I can send 50 coins? So this is the probing attack, which leaks different properties on the network. The first one is that it leaks the current liquidity of the channel. It leaks the existence of the transaction and the size. If the attacker will do that to many channels in the network, it also leaks what are the identities of the party, who paid whom. And it's actually silent to both Alice and Bob because he is not communicating with them. And this is the problem that our system, Twilight, is trying to overcome. So Twilight is a payment channel network, a new payment channel network, that utilizes noise in order to provide differential privacy guarantees. We also use trusted execution environments to deal with selfish relays. All the terms that are currently underlined will be explained later in this talk. In our paper, we also did both analysis and simulations to the 3 properties of cost, privacy, and security, and we did a full prototype implementation. Awesome. So in this track, happily, I don't need to explain what differential privacy is, but I do want to highlight our goal. Our goal here is that the attacker will not be able to distinguish between 2 events. The first event is that Alice paid Bob, and the second event is that Alice didn't pay Bob. We have the epsilon delta differential private definition that we all know. And in our paper, we actually did a full analysis, and we were able to provide an epsilon, a numerical epsilon and delta guarantee to the users of Twilight. Noise in our case is simple. In our case, noise is just a random number. I will not tell you now how we generate this number. But the idea is that we use it upon a request to the relay. When we got the request, hey, can we transfer M coins? The answer will be whether the liquidity minus this random number is big enough to transfer these M coins. And note that a naive solution here to how to generate this noise is not good enough, right? Because the attack is cheap. So the attacker can just query the channel over and over again, observe some kind of percentage of how many yes and how many no's he gets, and therefore he can just rebuild the histogram of the noise and know exactly what is the real liquidity. So we had to use something that is more complex. We used here a paper that was presented in 2011 that provide differential privacy guarantees under continual observation. The base idea here is that the noise is dependent on time. So here we're utilizing a thing that is called minimal covering set. So for example, if we had a transaction, if we had a coin transfer at a specific time at t equals 1, and the attacker queries the channel at t equals 2, then we will use noise that we will use the minimal covering set of the time span until this time of the query. So in this example, the node that is now rounded in blue is the node that we will use to derive the noise. If the attacker then queries in the next timestamp, then we will use the minimal covering set of the whole period. So as you can see here, we used the same noise twice. And because we use the same noise for every node, we used the same noise to hide the same coin transfer, which means that the attacker sees less different samples of the random generator that hides the same coin. To conclude, in order to answer the question, can we transfer M coin, we now need to consider the time of the query, and then we will just reduce the total noise of the nodes in the minimal covering set. There are much more details in the paper, I'm promising you. Cool. So as you can see, adding noise means that we need to lock more coins. In the example that I'm showing here, in order to achieve an epsilon which is 0.15, each relay needs to lock much more coins. In this example, it needs to lock extra 9,500 coins in order to hide this transfer, this one coin transfer. But please note that these locked coins need to be acquired when we're creating the channel. But then when we're destructing the channel, we get all this noise back, all these coins back. So therefore, if we, for example, if the relay will take a loan when you're creating the channel, and then will repay the loan when you're destructing it, he will only need to pay for the interest. And in our paper, we actually showed that given that the relay will do at least 77 payments a day for this channel, so with just 1% of fee, he will cover all the extra privacy cost. Great. Another thing that I want to highlight here is that relays are selfish. By being selfish, they just have the incentive to not add the noise. By adding noise, they're saying no to more transactions, to more payments that they need to handle. And they don't want to do it. In our paper, we used TEEs, trusted execution environments, in order to force them to add this noise. TEEs are isolated hardware that gives us the properties of confidentiality and integrity, which means that the relay cannot change the code that runs inside the TEEs, but it also can't see the memory or can't see which flow of the execution has been occurred. In our system, we actually decided to do a stateless trusted execution environment. And this decision has pros and cons. The big pro is that we don't need to handle the consensus and to handle the network protocol of the blockchains, but it also gives us great challenges. One example challenge is that the relay, because it is stateless, the relay can just re-execute it over and over again until he will see the result that he wants. We solved all this challenge and many more in the paper. I really encourage you to read it. We also provide a full prototype implementation to our system. This is currently an open source that you can all just gather and see. This is a huge repo. And we got a pretty good performance. Considering the throughput, we handle up to 850 payments a second, while currently the Lightning Network handles 350, which is almost 3 times. The latency for 4 intermediate relays is around 1 second, which is, I would say, sufficient when you try to pay someone. So to conclude, we were able to achieve differential privacy guarantees to Twilight using under continual observation of the attacker. Privacy is something that we're able to provide, but it comes with a cost. Relays has an incentive to not add noise, and we're able to force them using trusted execution environments. And we provide a full prototype implementation. Thank you.